Today, let's talk about bubbles, planets, and mountains. At first glance, these might seem completely unrelated. But what if I told you they share a fascinating connection? Curious? Let's dive in. Let's start with bubbles. They are tiny pockets of air trapped inside a thin layer of water and soap, held together by a force called surface tension. Pure water alone can't sustain a bubble, it's too tightly bound. That's where soap comes in. Soap reduces this water's surface tension just enough to make bubbles possible. But here's the big question. Why are bubbles always spherical? Why not cubes or pyramids? The answer lies in energy efficiency. Imagine a glass of water. Molecules deep inside the liquid are surrounded by other water molecules, balancing the forces acting on them. But at the surface, the molecules face an imbalance. They are pulled inward by neighboring water molecules, but experience no force from the air above. This imbalance leaves the surface molecules in a higher energy state. To reduce this instability, the liquid minimizes the number of surface molecules, and that means reducing the surface area itself. A sphere of all shapes has the smallest possible surface area for any given volume, making it the most energy efficient shape. That's why bubbles, and even water droplets, naturally form spheres when left undisturbed. But this isn't just about bubbles. The same principle of energy efficiency applies to something far larger: planets. Think about Earth, or any other planet in our solar system for that matter. Why are they all spherical rather than cubes? The answer once again comes down to minimizing energy. Here, gravity plays a similar role to surface tension. It pulls the matter inward, evenly in all directions towards the planet's center of mass. Over time, this force shapes planets into spheres, so whether it's a tiny bubble floating through the air or a massive planet orbiting a star, nature seems to have a preference for spheres. But what about mountains? They are anything but spherical, sharp, jagged, and uneven. At first glance, they seem to defy the universe's tendency for smooth, energy-efficient shapes. Yet even here, the principle of energy minimization is at work. Gravity pulls on mountains just like everything else. Peaks, being farther from the Earth's center, exist in a slightly higher energy state. Over time, natural forces like wind, water, and ice wear down these peaks, eroding them into lower elevation. This erosion redistributes energy, breaking down higher energy states into lower and more stable ones. Given enough time, mountains can flatten into plains, aligning with the universal rule of efficiency. So, if nature strives to minimize energy, why do mountains exist at all? It's because of immense geological forces at play. When tectonic plates collide, they push rock layers upward, creating towering peaks. Volcanic activities also form mountains, driven by heat and movement deep within the earth. While gravity and erosion constantly work to wear down the mountains, the geological forces that created them don't disappear overnight. This balance between creation and destruction is why mountains persist, despite nature's pull towards energy efficiency. From bubbles to mountains, the universe reveals an incredible harmony driven by simple yet profound principles. This interconnectedness reminds us of nature's elegance. Complex forms and processes emerge from straightforward rules. Perhaps by understanding these connections, we can better see ourselves as part of something greater.